Hello everyone, welcome back. Today we're going to talk about element number 98, Californium. Here we have Californium, and here we have the element symbol, Californium. Here's the Great Seal of the state of California, Eureka. Glenn Seaborg is a name you run into a lot around this part of the periodic table. He is on the list of those credited with the discovery of californium and also plutonium, element number 94, americium, element number 95, curium, element number 96, berkelium, element number 97, einsteinium, element number 99, fermium, element 100, mendelevium, element 101, nobelium, element 102, and seaborgium, element 106. The last one, seaborgium, is of particular note because it is the only really unambiguous case of an element named not only for a person involved in its discovery, but also for a person who was not dead yet. This was so controversial that the 1997 agreement to allow it was reached only after a horse trade in which Seaborg's colleagues at the University of California, Berkeley, allowed their arch-rival, the Joint Institute for Nuclear Research in Dubna, Russia, to pick the name for element 105, which both groups claim to have found first. And that is how it came to be that we now have both seaborgium and dubnium, element 105, though it is said that, to this day, some people at Berkeley refuse to call 105 by its official name, dubnium. The naming of einsteinium and fermium might have been similarly controversial, but for the fact that Cold War secrecy kept their discovery and their proposed names secret for so long that both Albert Einstein and Enrico Fermi had conveniently, if unfortunately, died by the time the existence of their elements could be revealed. According to the author, I promised application examples for californium, the last element that has any whatsoever. Californium is an extremely powerful neutron emitter, a property that makes it both extraordinarily dangerous and uniquely useful. Of all the forms of radioactivity, here we have beta decay. Beta minus decay happens when an atom has more neutrons than protons. To gain stability, a neutron becomes a proton and an electron. The proton stays in the nucleus while the electron beta minus particle is emitted. Because the atom gains a proton and loses a neutron, its atomic number increases by 1. The mass particle number stays the same because the number of nucleons stays the same. Beta plus decay, positron emission, happens when an atom has more protons than neutrons. To become more stable, a proton becomes a neutron and a positron is emitted. Because the nucleus loses a proton and gains a neutron, its atomic number decreases by 1 and the atom becomes a different element. The atom still has the same number of nucleons though, so the mass number stays the same. In summation, beta rays. Beta radiation. Beta radiation occurs when an atom decays by giving off a high-energy, high-speed particle that has a negative or positive charge. These beta particles are both smaller and more energetic than alpha particles. There are two types of beta decay. When a negatively charged particle is emitted from the nucleus, it is called beta minus decay. The negative beta particle is also called an electron, but it originates from the nucleus, not the electron cloud surrounding the atom. When a positively charged particle is emitted from the nucleus, it is called beta plus decay, or positron emission, because the positively charged particles are called positrons. They have the same mass as electrons. X-rays. X-rays are stopped by dense materials like bone, tumors, or lead. This makes them useful for medical diagnosis. Gamma radiation and X-rays are high-energy waves that can travel great distances at the speed of light. Both can penetrate deeply into matter. Alpha rays. Alpha radiation. Alpha radiation happens when the unstable atom emits 2 protons and 2 neutrons, basically a helium nucleus. The original atom with fewer protons and neutrons becomes a different element. Compared to other forms of ionizing radiation, alpha particles are large and heavy. They can't travel very far, so they are useful in things like smoke detectors. They can be stopped by a piece of paper, your skin, or even just a few inches of air. Gamma rays. Gamma rays can penetrate further with higher energy. Gamma radiation can be used to precisely target and eliminate tumors. It also has a number of uses in industry, agriculture, pest control, and more. Gamma rays can be stopped by several inches of lead. And finally, the neutron rays that Californium emits. Neutron rays. Neutron radiation. Neutron radiation is created as a result of fission reactions and happens in nuclear reactors, or in this case, because we're talking about Californium, from the emission of element number 98, Californium, from its nucleus. Neutrons are extremely high energy, so need many feet of dense materials like water or concrete to stop them. Neutron radiation can make other materials radioactive and is used to create the radioisotopes used in medical treatments. Neutron radiation. Again, as a quick review, there are 4 basic types of ionizing radiation: alpha, beta, gamma, and in this case, Californium, element number 98, its emission is neutron radiation, and each has unique properties as we previously discussed in this video. Neutron radiation, again, can make other materials radioactive. In the case of gold, it makes it radioactive, so it emits gamma radiation, and built-in detectors with the Californium detect the radiation, the gamma radiation, and they know that it's gold. Again, of all forms of radioactivity, the most dangerous is neutron emission. Because neutrons carry no charge, they are not repelled by either negatively charged electrons or positively charged protons. This allows them to pass through solid matter with relative ease. If they should happen to strike a nucleus, they are able to infiltrate and destabilize it. A beam of neutrons thus has the alarming property of converting perfectly ordinary matter into radioactive isotopes. Exposed to neutrons, you yourself become radioactive, with a half-life of 15 hours, primarily from the sodium, element 11, isotope 24, symbol 24Na. Is neutron radiation the most dangerous? Neutrons readily pass through most material, but interact enough to cause biological damage. Due to the high kinetic energy of neutrons, this radiation is considered to be the most severe and dangerous radiation available, according to wikidoc.org. Neutron radiation. Can neutrons hurt you? These neutrons can either cause cells to change in their functionality or to completely stop replicating, causing damage to the body over time. Neutrons are particularly damaging to soft tissues like the cornea of the eye, according to Wikipedia. Neutron radiation. Neutrons are particles and are very penetrating. Several feet of concrete or another material rich in hydrogen, such as water, are required to stop them. Neutrons are a radiation hazard for the entire body. Neutrons interact with tissues in the body and have the potential to cause damage, according to www.co.monmouth.nj.us. Radiation Health Basics. What makes neutron irradiation useful is that when a given element is turned radioactive and then decays, the type and energy level of the resulting radiation is highly characteristic of that particular element. For example, if you beam neutrons at a piece of rock and get back gamma rays of a particular energy, you can say for sure that there is gold, element number 79, inside that rock. This technique is called neutron activation analysis. And besides detecting gold, it can identify oil in the bottom of a well or explosives inside a shipping container or suitcase without having to open either. Californium-252 is a very strong neutron emitter, giving off approximately 139 million neutrons per minute. This aspect, combined with Californium-252's half-life of 2.645 years, melting point of 900 degrees Celsius, and easily cut form, makes this neutron source very useful in a variety of industrial applications. Californium-252 cannot be found in nature, so it is produced synthetically by bombarding plutonium, americium, and curium with neutrons. If you're interested in learning about the elements americium and curium, I'll leave a link in the description below, and I'll talk about the element plutonium in a future video. Various applications of Californium-252 include initiating nuclear reactions for nuclear fission by providing the neutrons to bombard originally with the uranium and other fissionable elements, material scanning through prompt gamma neutron activation analysis, PGNAA, and well logging in the oil and gas industry. When Californium-252 is implemented within military and defense equipment, it enables the use of portable isotopic neutron spectroscopy (PINS). PIN systems typically use Californium-252 to identify explosive devices, weapons, and more, specifically by analyzing the gamma ray signatures of the target's contents. So again, this technique is called neutron activation analysis, and besides detecting gold, it can identify oil at the bottom of a well or explosives inside a shipping container or suitcase without having to open either. Quick review. Neutrons can see straight through the solid steel hull of a ship. What Californium does is provide a convenient, very small, very portable source of a whale of a lot of neutrons, one that can be deployed in portable inspection instruments such as those that are lowered down oil wells, seen here. Circulating water, neutrons, aluminum basket, neutrons, aluminum pot, and a sample of oil. Again, quick review, Californium is used in neutron radiography for the detection of corrosion in metal aircraft parts. It is also used in metal detectors to find gold. It is used to detect explosives. How is Californium-252 used in airports? Californium-252 is used as a source of neutrons to excite nitrogen, which is commonly found in explosives. The excited nitrogen-15 undergoes radioactive decay by emission of 10.8 megaelectron volts of gamma rays. The gamma rays are detected and configured by an array of scintillation detectors on 3 sides of the baggage. According to www.nrc.gov, HPPOS 196, explosive detectors for use at airports, nrc.gov. So explosive detectors use radioactive element number 98, Californium, to emit neutrons and to make the nitrogen radioactive, which is found in the dynamite, and then it emits gamma rays that the detector detects and says, hey, there's nitrogen in there, which means that there's explosives in there, which means that that person is carrying a bomb. Get him! Now say goodbye to any form of usefulness. After Californium, it is safe to say that the people and places for which the remaining elements are named are far more important and more interesting than the elements themselves. The most spectacular example of this principle comes in the case of Einsteinium. But for now, let's continue with element number 98, Californium. What is unique about Californium? Californium is a malleable and so soft metal that it can be sliced with a razor blade. Its spectrum has been observed in supernova. 22 grams of Californium cost 22 million pounds, one of the most expensive substances in the world, according to www.ccdc.cam.ac.uk. So in case you were thinking of obtaining Californium to look for gold, in order to obtain sufficient amounts of Californium to make a sufficient detector, you would have to spend a lot of money to create a device that looks for gold, which would be counterintuitive. Californium, the Cambridge Crystallography Data Center, CCDC. Why is the decay of Californium important? In particular, with the isotope Californium-252, alpha particle decay is important because it determines the half-life, but the expected applications of the isotope exploit its spontaneous fission decay that produces an enormous neutron output, according to Britannica.com. So in other words, it emits a lot of neutrons when it decays. What type of radiation does Californium emit? Californium-252 is a man-made radionuclide with a half-life of 2 to 65 years, which emits a mixture of neutrons and gamma rays, both highly energetic radioactive emissions. It is used in radiotherapy as an alternative to radium and extends the potential benefits of neutrons to interstitial and intracavitary applications, according to pubmed.ncbi.nlm.nih.gov. The potential of Californium-252 in radiotherapy, preclinical PubMed. Why is Californium used in bombs? The compound Californium-251 has been seen as a potential use for nuclear weapons as it has very low critical mass, high lethality rate, and short period of toxicity to the environment as opposed to other radioactive elements, according to www.earth.com. Earthpedia articles. Californium. What is Californium? Is Californium used in atomic bombs? Californium is used in the manufacture of the nuclear bomb, but is also used in running a nuclear plant. This material was synthesized for the first time in 1950 in the California University, according to newscast pratashka.com. Apologies for the incorrect pronunciation. Smuggling of californium used for nuclear bombs in Turkey. Californium, element number 98, the actinoid elements. Its symbol is CF, its atomic number is 98, its atomic weight is 251.08, its color is silvery, its standard state is solid at 25 degrees Celsius or 77 degrees Fahrenheit. Its classification is metallic. You are here on the periodic table. Here we are. Born in the Golden State, I'd love to be laid back, but the problem is my chilling ability to release streams of neutrons from my atomic nucleus. My ferocious rays can pass through an object as if it weren't there, leaving everything in its path radioactive. My neutron beams are used to kickstart nuclear reactors and to detect oil and gold. Californium's date of discovery was in 1950, or its date of creation, however way you would like to look at it. Californium's density is 15.1 grams per centimeters cubed. Its melting point is 900 degrees Celsius or 1,652 degrees Fahrenheit. Its boiling point is unknown. Californium, element number 98, symbol CF. This element was named after California, the US state where it was first made. Californium is a raw material used for making very heavy elements, such as oganesson. It is one of the world's most expensive substances. A gram of californium costs $27 million. This is because it is difficult to produce this highly radioactive element, making it rare. Its atomic mass is 251, its state is a solid, and its discovery was in 1950 by Stanley Thompson, Kenneth Street Jr., Albert Ghiorso, and Glenn T. Seaborg. 1 gram of californium costs $27 million because it is difficult to produce. Kenneth Street Jr. Kenneth Street Jr. was an American chemist. He was part of the team that discovered elements number 97 and 98 in 1949 and 1950. Street was born in 1920 in Berkeley, California. He obtained his degree in chemistry in 1943 from the University of California, Berkeley, according to Wikipedia. Glenn T. Seaborg. Here's some information on Glenn T. Seaborg, previously mentioned. Californium, element number 98, symbol CF. Named after the state of California, californium was discovered in 1950 by the American scientists Stanley Thompson, Kenneth Street Jr., Albert Ghiorso, and Glenn T. Seaborg. This radioactive element is used in the treatment of cancer. It is also used in portable metal detectors. Artificial creation. These pellets of californium were refined in a laboratory. The element is not found in nature and is created artificially by smashing atoms of berkelium with neutrons. Berkelium is element number 97. I'll leave a link in the description below if you're interested in learning about element number 97. Here we have element number 97, berkelium. You get californium, element number 98. Here's a pellet of californium. Californium is a very strong neutron emitter. It is used in portable metal detectors for identifying gold and silver ores, to identify water and oil layers in oil wells, and to detect metal fatigue and stress in aeroplanes. Californium-252, because 3% of its decay occurs by spontaneous fission, is industrially and medically important as a very intense source of neutrons. 1 microgram releases 170 million neutrons per minute. Californium was first made in 1950 at Berkeley, California by a team consisting of Stanley Thompson, Kenneth Street Jr., Albert Ghiorso, and Glenn Seaborg. They made it by firing helium nuclei alpha particles at curium-242. The process yielded the isotope californium-245, which has a half-life of 44 minutes. Curium is intensely radioactive, and it had taken the team 3 years to collect the few milligrams needed for the experiment. And even so, only a few micrograms of this were used. Their endeavors produced around 5,000 atoms of californium, but there was enough to show it really was a new element. Californium, CF, synthetic chemical element of the actinoid series of the periodic table, atomic number 98. Not occurring in nature, californium, as the isotope, californium-245 was discovered in 1950 by American chemists Stanley G. Thompson, Kenneth Street Jr., Albert Ghiorso, and Glenn T. Seaborg at the University of California, Berkeley as a product resulting from the helium-ion bombardment of curium-242, atomic number 96, in the 152-centimeter, 60-inch cyclotron, followed by chemical separation from other elements by chromatography. The element was named after the state of California where it was discovered. Californium, a useful radioactive element because it emits neutrons. 170 million neutrons per minute is approximately 2,833,333.33 neutrons per second. Now, since neutrons are, well, technically they can be split from a neutrino, but since neutrons are individual particles, they can't be fractions, or else they wouldn't be the neutrons that we classify them as. Estimated. Natural abundance. Californium did not exist in weighable amounts until 10 years after its discovery. It is prepared in milligram amounts only by the neutron bombardment of plutonium-239. We'll talk about plutonium in a future video. The image is based on the state flag of California and features a grizzly bear, a symbol of great strength, and a lone star. All californium isotopes are radioactive. The long-lived isotopes are produced from berkelium-249 or from californium-249. They are californium-249, which has a half-life of 351 years, californium-250, which has a 13-year half-life, californium-251, which has a half-life of 898 years, and californium-252, which has a half-life of 2.645 years. The isotope californium-249 has been used in tracer levels and microgram amounts to investigate the chemistry of californium, which exhibits an oxidation state of +3 in aqueous solution, and for preparing microgram quantities of compounds such as the oxychloride CfOCl, the oxides CF2O3, and CfO2, and the trichloride CfCl3. CfOCl is a combination of californium, oxygen, and chlorine. Californium CF2O3 is a combination of 2 atoms of californium bound to 3 atoms of oxygen. And CfO2, 1 atom of californium bound to 2 atoms of oxygen. And the trichloride CfCl3, 1 atom of californium bound to 3 atoms of chlorine. The dihalides CfCl2, CfBr2, and CfI2 have been made. There is also some evidence from electrochemical studies in solutions for a +2 state. Metallic californium has been prepared and is structurally similar to metallic americium, curium, berkelium, and most lanthanoid metals. Here we have californium oxychloride. Californium oxychloride is a radioactive salt first discovered in measurable quantities in 1960. It is composed of a single californium cation and oxychloride consisting of 1 chloride and 1 oxide anion. It was the first californium compound ever isolated. Here we have californium chloride. Californium-3 chloride. Californium-3 chloride is an inorganic compound with a chemical formula CfCl3. Like in californium oxide and other californium halides, including californium fluoride and iodide, the californium atom has an oxidation state of +3. According to Wikipedia. Its molar mass is 357 grams per mole, and its classification is an inorganic compound. Here we have californium-3 chloride. Here we have the molecule. 3 chlorine atoms combined to 1 californium atom. Californium-2 iodide, CfI2, is a deep purple solid with a stable rhombohedral structure at room temperature and an unstable hexagonal structure. Californium-3 iodide, CfI3, is a lemon yellow solid that has a rhombohedral structure and sublimes at 800 degrees Celsius, according to Wikipedia. Here we have californium-3 bromide. Californium-3 bromide is an inorganic compound, a salt with a chemical formula CfBr3. Like in californium oxide and other californium halides, including californium-3 fluoride, californium-3 chloride, and californium-3 iodide, the californium atom has an oxidation state of +3, according to Wikipedia. Its chemical formula is Br3CF, 1 atom of californium bound to 3 atoms of bromine. This is CfF2. Let me present CfI2 and CfI3. So here we have californium-2 iodide and californium-3 iodide. So here we go. Here's the correction. Instead of californium, here we have CfF2. It's actually californium iodide, CfI2, and CfI3. Here we have the atoms, the molecules, and if it were to be bound with fluorine, it would actually be bound to 3 atoms of fluorine and 4 atoms of fluorine, as seen here. Californium 3 fluoride, CFF3, is a yellow-green solid with a crystal symmetry that gradually changes from orthorhombic to triagonal when heated above room temperature. Californium 4 fluoride, CFF4, is a bright green solid with a monoclinic crystal structure, according to Wikipedia for both. So that was Californium explained in the next minutes or less and as a short amount of time as possible. Once again, if you like this video, make sure to like, comment, and subscribe. Other than that, thank you everyone for watching. Stay tuned for the future videos. Have a great one.